So I want to share with you a personal story. OK， 我就讲中文好，我就讲一个，因为有时候我觉得大家会因为某个科目考好，就对某个就觉得说我比较在行啊，某个科目考不好，就说我跟这个没有缘分啊。Don't say that too early. OK, so it happened to me. When I was at Stanford, so we all had a PhD qualifying exam. So I aimed for PhD when I arrived at Stanford. And the quality in the 资格考啊，博士班资格考 PhD qualifying exam. So the rules were we all need to meet with, each of us meet with 10 different professors. 每个同学要去跟，你可以选志愿啊。You need to talk to 10 different professors and they'll test you. They'll give you a few questions and you need to answer them in 10 minutes. So 10 meetings of 10 minutes is very stressful. 非常有压力啊，你一 stuck 就觉得完蛋了啊。So luckily I passed the first time. But there's one professor who gave me 3 out of 10. 就是满分10分，有某个 professor I still remember his name. His name is Fabian Peace. Okay, I can say that. So you remember like tough professor for a long time, Fabian Peace. I still remember his name. Fabian Peace, whose specialty is E-beam lithography. Lithography 半导体制程啊，physicist. Yeah. Professor Fabian Peace gave me only 3 out of 10. After meeting with him, he gave me a hard time. Luckily, I still passed. So I tried to avoid taking his class ever. But then, quite a few years later, 6 years later, it took me 7 years to finish my PhD. Okay, finally, when I was about to arrange for my oral defense, 口试要安排嘛 and at Stanford, the department required us to find a professor that is out of your field, absolutely out of your field. Okay, and my field is signal processing, right? So semiconductor manufacturing is absolutely out of my field. So I had a far time to, we need to find that one professor to chair our oral defense. 那个主席必须是 out of field. 你不可以说就找老师熟悉的老师啊，不行。You need to find somebody out of your field to chair your oral defense. 这样了解吗？啊。And Stanford professors were all super busy. So I sent email. I even asked 我的硕士班导师啊，他不理我。Yeah. So I had a hard time. I sent emails. I sent invitation to, I think, almost 20 professors, but they all said that they either didn't reply or they reply like immediately that they are too busy. They had no time. That's how busy they are. So I couldn't find anybody, so I seek help at the department office. 我去系办问是否系办的姐姐可以帮我一下，推荐有哪些老师可能可以找。他就看一下，你领域是讯号处理。How about Professor Fabian Peace 然后我就心里面就冒冷汗，我就是 he's probably the last person I wanted to find. But then I sent him an email, yeah, and immediately his secretary replied, Professor Peace he does not have time. But I sent a very interesting email, okay? But so later at night, Professor Fabian Peace replied. 他就是等于否决他秘书已经回信给我了，就说老师没时间。不过后来稍晚他回信给我，他说他有时间了，因为他看了我的信觉得很有趣。What did I write? I said, Professor Fabian Peace, you hold a special place in my heart because you gave me 3 out of 10 when I was doing my PhD qualified exam. I remember you for that. So you hold 你在我心中是有个很奇特的地位在那边。他就说他任教20年，从来没有看过有人这样写。通常大家写给老师，因为我都拿10分，我拿 A+，所以我希望 Can I have the honor to invite you？ 一般人都是用很客气，觉得都是 honor， 但是我是拿我最烂的 performance 来跟他做 sharing， 结果他就说他这太奇特，他一定要 host 我，所以他就回信说他可以。后来我的口试他帮我大忙啊，帮我非常大的忙。So never say never, okay? Even before I did my oral defense, he invited me to give a 20-minute version, a condensed version of my presentation to his group. And everybody's out of my field, so I get a chance to practice, to rehearse my talk. It's really helped me a lot. I still remember him. Okay, so 如果考坏了啊，没关系，过几年想要找我帮忙，就是说老师，我当初期中考56分。 and you hold a special place in my mind. So I will help you. 好吗？ So don't be feel too bad. Okay, never say never. Okay, so enough of my personal sharing. Fabian Peace, nice guy, decent scholar. Okay, let's come back to big omega and small omega. Okay, so now we have a relation between the small and the big omega. Okay, and one of you actually asked a very good question. So in the beginning of this semester, right, I was talking about there's a simpler relation between big and small omega. Okay, what is that? That is when we talk about sampling, right? We talk about discretizing our time axis. Okay, so we go from a continuous time function to let's say when we do A to D conversion, we receive an input which is continuous in time, and then it produces an output with a sampling period, right? And the output is x of n equals to x continuous time evaluated at n times big T, right? So if we do that, then now we go to a frequency domain. There is a simple relation between big and small omega. That's in this context. In that context, what's the relation? Anybody remember what's the relation between big and small omega in this context? The relation goes big omega equals to small omega divided by t, right? That's when we talk about sampling a signal, okay? But now we have a different relation because the context is different. Now we are designing a filter, okay, by borrowing an analog prototype. So we are not talking about sampling. We're not talking about sampling, so it's not surprising that we have a different relation. It's just still using the same variables, the same notation, but now the context is different. Okay, so let's be clear that we know the difference in. We have two different contexts. Okay, filter design versus sampling a signal. Okay, this is about designing a system. This is about sampling a signal. Okay, system versus signal. So two different contexts, two different contexts. 情境不一样，我们用情境不一样。So let me clarify that. But now coming back to focus on this equation right here, big omega as a function of small omega. Now we have, and this relation explains why the relation between analog prototype and its discrete time design. So really, long story short, it's about compressing the frequency axis. Let me repeat, compress, 压缩. It's about compressing the frequency axis. In what sense? So now, the analog prototype, in the analog world, the frequency omega can go from DC, from 0 to infinity. So that's the entire frequency axis from 0 to infinity. But now, by using arctangent, the corresponding small omega. So let me erase this discussion over here. By using arctangent basically compresses the entire real line to a finite interval, right? So here we have a situation that small omega is 2 times arctangent of TD divided by 2 omega, big omega, right? And arctangent basically does the compression job. It maps the entire real line to somewhere in between plus pi and minus pi, because we have a factor 2 here, right? Other arctangent is from pi over 2 to minus pi over 2. With a factor of 2, now this is exactly what's happening. The entire frequency axis is now mapped to the finite interval between minus pi and pi, and the slope here depends on this parameter TD, okay, which is not that important. So with this idea, so now that we understand it's a compression of the frequency axis, now we can see what will happen as far as the frequency magnitude response is concerned. Okay, so now we say that h of s of z is our desired system. Therefore, the frequency response now as a function of small omega is a composite function of h of omega of omega. H of big omega of small omega. Okay, so what does that mean? So that means that at every frequency, let's say this frequency, corner frequency, oh, by the way, notation is still a bit different. Here, the h here is my g, okay? And the hc here is my h. Sorry for the confusion, okay? This is a direct copy from the textbook. Okay? 把它写下来好, yeah. So here on this slide, or let's just simply draw it. So now, if you want to understand what is g of ej omega at any omega right here, okay? So in this plot, we have the relation of tangent. Now this is pi, and tangent goes like that, okay? Asymptotically approaching infinity, okay? At exactly pi, because big omega is what? Is this factor tangent of small omega divided by 2, okay? That, yeah. So that's the mapping, the compression. Okay, so now if you want to understand for any omega, what will be the frequency response? You can just go, first of all, just find out omega, and this is going to be, here is going to be big omega of small omega, okay, along this axis. So that's why here on the textbook, we have this drawing. Now, if we just rotate the frequency response plot by 90 degrees right here, just do a 90-degree rotation. 90-degree rotation, 转过来嘛, turn it 90 degrees, then here we have the magnitude response, which is our prototype, h of j big omega, as a function of omega. Okay, and what's our prototype? If our prototype is Butterworth, if our prototype is Butterworth, then let's say the Butterworth has a corner frequency right here, and it's almost flat, and then you reduce to 1 over 2, 1 over square root of 2, and they drop like that, right? So that becomes our prototype. And if you just plot it by turning it 90 degrees to counterclockwise, then to evaluate the resulting system, the resulting frequency response now as a function of small omega, just first choose any random omega right here and find out big omega, the corresponding big omega, and then the big omega right here goes here, right? And then what is this? This is a gain. Is that clear? So for every so it's a DC, go to DC, go to DC, and the gain is 1. Okay? Corner frequency, and then it goes both ways, actually. Corner frequency, no, this big omega C. Corner frequency right here, corner frequency right here. So you can go freely between big omega and small omega. Okay? So corner frequency right here, small omega C. We know that right here, the gain should become 1 divided by square root of 2, and so on. So now, still, let's take a plot of a few more points, okay? Now, yet another frequency, small omega going up, big omega right here, here. So the gain is that much. Okay, the gain is somewhere like here. and so on. So let's move further to the right. How about this frequency? This frequency goes here to top. That frequency goes here. Oh, the gain is very small. So that's a way. So you can just keep adding more and more points, and then turns out so you get this frequency response, which will also be monotonically decreasing if your prototype is Butterworth. Okay. So in this sense, by just keep plotting more and more points, you'll figure out that indeed you begin with an analog prototype and you end up with a digital filter design. And the general shape will be the same. The only difference is a compression of the frequency axis. Okay? Now the frequency axis originally is from DC to infinity, but now we compress it to the finite interval between 0 and pi, which is exactly what a frequency response ought to be defined over the region of 0 frequency DC and pi, the Nyquist rate. Huh? So is this good? Huh? So I want to share with you this is why bilinear transformation gives us a design of a digital filter. Okay, design of a digital filter, monotonically decreasing here in one originally, monotonically decreasing after the design. Okay, this nice property is preserved. Nice property is preserved. Yeah. Any question regarding this slide? Yeah. Please make sure that we understand what's going on right here. Okay, it's going in between small omega and big omega using this relation, this tangent relation, and you'll be able to find out the frequency response given its prototype. Okay, given its prototype. One-to-one mapping. Okay. Okay, so with that, I would like to provide you some extended reading materials. Okay, some extended reading materials. So I didn't know it, but I did my homework. So the Butterworth filter historically was constructed really early. Butterworth, according to Wikipedia, okay, Butterworth was a British engineer and physicist, Stephen Butterworth, okay? So he was interested in designing an analog circuit which has the maximally flat frequency response, but yet providing a low pass characteristics, okay? So he figured out that if we just put one resistor, capacitor, and 2 inductors like that, and by carefully setting the parameters, the resistor has, if the resistor is 1 ohm, and the two inductances are a few, like 3.5 or 1.5 Henry, Henry, okay, right, Henry, H is Henry, right? And if the capacitor is 4/3 farad, then you can show that the transfer function between the output and input, that transfer function turns out to be that of a third-order Butterworth. Okay, to be third-order Butterworth. So historically, it's about circuit design, and you can generalize. So if you're interested, there are some further readings you can find from Wikipedia. And my next comment is, this is just optional, okay? Just reading materials also in the appendix of our textbook. So it turns out that we have a few different designs, okay? In one design, we can allow the passband to have ripples while the response decreases monotonically after the corner frequency, okay? There exists such kind of analog prototype, and the name is Chebyshev filter. Okay? And in Chebyshev filter, the the magnitude response has this also pretty nice expression, monotonically decreasing after when omega is greater than omega, the corner frequency. Okay, so here Vn is the nth order Chebyshev polynomial. It's a polynomial. So that's kind of a generalization from Butterworth. Generalization from Butterworth. Okay, only this term is more complicated. So as a matter of fact, now the passband can have ripples, yeah, whereas the stopband has a nice monotonically decreasing magnitude response. Chebyshev filter using Chebyshev polynomial. And a bit more further than that, there's even a thing called elliptic filter. Elliptic, the 椭圆 and now on the right, both the passband and the stopband, now both of them can have ripples. Okay? So in general, so you may ask, why do we want to allow ripples there? Why do we want to allow ripples there? Ripples are not good, right? Being maximally flat is wonderful. Why do we want to consider having ripples? So that may be a question to ask, right? That may be a question like, why do we need to consider allow ripples? Is there any advantage? Right? But these are like extended reading materials that you can find in the textbook. So in case you're interested, go ahead and read it, where you'll find that elliptic filter. Here we have an expression right there. U is a Jacobian elliptic function. Okay? And I have no idea what that is. I tried to learn it, but I searched the Wikipedia. It's very complex. 椭圆函数. I've never encountered it in my career. So, has anybody encountered elliptic function in your career? You don't have a career yet. Maybe. So I had no idea, frankly, what a Jacobian elliptic function is, but extended materials can be found in the textbook. And with that, let's end our discussion for this lecture. Right. So let's take a short break. I'm going to switch to my next presentation. Take a 2-minute break.其实我真的觉得我蛮可惜，我那个大学时候大3时候的那个电子学没有拿到90分啊，从此我就觉得我跟电子学无缘了，所以也没有去修 VSI， 也没有修 analog， 我觉得很可惜啊，我现在想起来觉得蛮可惜啊。Don't be like me, right? Be courageous, stay curious 啊。Stay curious and stay， 你要常常给自己打气啊！要常常你们每个人都要学会给自己打气啊！真的啊 ，Life will be fine， 对，Life will be fine。好 ，any 还有呀 ，OK， so。再1分钟啊！那个另外一件事情I want to communicate. So for Thursday music, so far, I found that a lot of you like Japanese or Korean songs, which are okay, but 有点大家选的音乐音量偏比较大啊。So tomorrow I'll ask the TA to play softer 音量要降低，不然的话，我觉得有时候。I was hoping that the music will help us focus. Okay, so please consider the kind of music that help you focus. Okay, and I preserve my own right to reduce the volume. 如果我觉得有点太嘈杂，我可能会请那个助教降低音量。I encourage you to find some all different kind of music. Right. There's no limit. Okay, you don't need to confine yourself to Korean or Japanese songs. Yeah. All right. So now with that, let's let's go for this next lecture, okay? Lecture 8. Now we are at FIR. FIR, finite impulse response filter design. And today, in this lecture, we'll focus on the window method. There's another method, okay? But today we focus on the window method. Outline, so kind of the most basic idea is to keep in mind that windowing refers to multiplying our ideal filter response with a window function. It's a multiplication in the time domain. So that's probably a take-home message. You're going to do what we are going to do is to multiply something with a window. Multiplication in the time domain. And this action can be also called windowing. So now window is a verb, okay? To window your signal, okay? Window is a verb. Windowing in time corresponds to convolution in frequency, okay? And this could be confusing. This could be confusing, okay? I want to make sure we notice this. Why do I say this could be confusing? Because what is a filter? Filter is convolution in which domain? In the time domain, right? So in order to design a filter which we use for convolution in the time domain, we apply multiplication in the time domain in our design process. And this design process results in convolution in the frequency domain, which is exactly the opposite. So I say this might be confusing. This might be confusing. Please still keep in mind that the result of our design is still an impulse response, which is supposed to convolve our input signal in the time domain. But it's just like when we design the filter, we apply multiplication in the time domain during our design, okay? And the kind of consequence is convolution in frequency. This we do know, okay? We know this because multiplication in time indeed results in convolution in the frequency domain. That's for sure. But the context你要稍微想清楚一点啊 could be confusing. And then outline number 2, in the design process, we will touch on this Gibbs phenomenon. Okay, we'll encounter Gibbs phenomenon. Okay, exactly how we'll see that. Okay, in the design process, we'll encounter Gibbs phenomenon. And then, unfortunately, Gibbs phenomenon gives us some limitation. Okay, so we need to consider how to. Gibbs phenomenon causes a ripple that cannot be suppressed. Okay, so in order to suppress the Gibbs phenomenon, suppressing the ripples, we need to carefully choose a window that does the job. Okay, and this part of I'm sorry that I apologize that the handout is still under construction, but here is the outline already. First, we talk about the basic concept. Then we talk about a problem that will be encountered, which is Gibbs phenomenon. And then after that, we introduce how to choose windows in order to suppress ripples. Okay, so first thing first. You have seen that this function, the sync function in time, in discrete time, this is the impulse response for an ideal low-pass filter which has omega c as its cutoff frequency. Okay, we have seen that quite many times. Already seen that many times. But as I introduced earlier in this semester, this ideal low-pass filter cannot be implemented. Why? First of all, this G of n is not causal, right? It's not causal because it has a negative time part. It's symmetric around time 0. So G of n is symmetric. It's going to be symmetric around time 0 with this kind of envelope, the envelope is that of a sync function. And otherwise, if we have a high sampling rate, we have a G of n. Do I call it G? Yeah, G of n. It's going to be an evenly symmetric function around time 0. And it also extends to the right and to the left infinitely. Okay, it's infinitely long, non-causal, and infinitely long to the right also. So it cannot be implemented, at least to the best of my knowledge. You will need infinite memory to store the entire waveform. So it cannot be implemented. Okay? So therefore, we suggest that it makes sense to truncate G of n. If this is our ideal filter, we know that it's ideal in the sense that after Fourier transform, the frequency response is low pass, okay, with a cutoff frequency at small omega c. It's an ideal that the gain is 1 in the pass band and 0 in the stop band, and this sharp transition. The pass band and stop band just 无缝接轨 just it makes an immediate transition from the pass band just immediately to a stop band. This is ideal, but this cannot be implemented. Okay? So therefore, there's a recommendation. Let's truncate. Let's simply keep the middle part. Okay? Let's say, all right, so sooner or later we're gonna disregard everything outside the range from minus n to plus n. We say that, okay, sooner or later we need to just ignore whatever that's outside this range. Truncation, 截断它, truncation. How about just keep the middle part? So by keeping the middle part, we mean we define a filter. Define a filter which now has finitely many samples, okay, many non-zero samples. It has is non-zero only in this region, okay, from minus n to plus n. Truncation, just set it to 0 everywhere else. Otherwise, in the middle, to the left by n and to the right by n, in this interval, in this region, h is exactly equal to g. Okay, it's a fair enough approximation. G goes on. Let's say G goes on, but H now is only defined between plus and minus n. And that in that way, we make a truncation. We choose only the middle part. That's the way I put it. 只保留中间, preserve only the middle part, okay? Symmetrically. So let's say we preserve from here to here. And turns out that we can already call this a design. This is already design, a very naive idea. 实际上蛮天真的啊 ，naive， 知道吗 ？Yeah. This idea might look naive. It's French, okay? 天真的啊 ，but actually it's a fair design. It's already a fair design. Seriously. So it means that if we have a filter that is like that, having now 2n plus 1 points, then now can we implement this filter? Yes and no. It's not causal yet, right? But we can shift it all to the right. Now redefine your time 0, right? Now this is the first sample. That one next to it is the second sample. You know what I mean, okay? This is something that can be stored in your computer. And if you allow a delay by n samples, this can be implemented. And it has finitely many samples, a little big, 2n plus 1, maybe 1,000 plus 1, okay? Maybe big, but it can be implemented by storing all the filter coefficients. Okay? Just create a long array and store every coefficient. It can be implemented, hardware or software. Okay? It's already not nice. Kind of this design is not bad. Okay, naive but not bad. So now let's say next we should examine the performance in the frequency domain. This is not going to be ideal anymore. Okay, then what's the resulting frequency response? That's the question we are asking. Right? It's not going to be ideal anymore, but how much does it deviate from ideal? So I may need to draw a bigger picture. I think I do. So let's try to investigate what's the performance, maybe I can just draw here. Yeah. If originally, now going from time to frequency using the Fourier transform, if originally the ideal response is just sharp transition, unity gain, zero passband gain whatsoever, no gain in the passband between minus cutoff frequency and plus cutoff frequency. That's the ideal response. Now we need to find out what will happen in the frequency domain after truncation in time. Okay? So the number one concept we need to notice is that by truncation in time, equivalently, we are multiplying the ideal response with a rectangular window. Okay? We're multiplying this response with a rectangular window. What is that? We will explain in the next slide. Okay? It's actually multiplication in the time domain. So in the next slide, I argue that truncation can actually be thought of as multiplying the ideal response with a window function. And what's the window function? The window function is all 1 between minus n and n, and 0 elsewhere. And 0 elsewhere. Okay? This is the window function that, so that when you multiply your ideal response with this window function, the resulting design is truncation. Right? Truncation means multiplying by 1 between minus n and plus n, and everywhere else is 0. Right? So just equivalently, truncation means that we are multiplying our ideal response with the window function. Okay? So can we agree on that? Yeah. That we are multiplying our, so this is W of n. So W of n is all 1 between minus n and n, including both edges, and 0 elsewhere. 0 elsewhere. That's our window function in the time domain, okay? From minus n to n. That's what's happening when we truncate, when we disregard all the extending samples of the ideal response. Is that clear? So now already we have a multiplication in time. So immediately we know that the frequency response, the Fourier transform of our design denoted by h sub n. N is the length, right? Which is a factor to choose. N is the length. The resulting, so by multiplying in two signals in the time domain, we are doing the corresponding change in the frequency domain is convolution. Okay? So now multiplication time, convolution in the frequency domain. Still, we retain this notation of small letters for time domain, big letters, capital letters for frequency domain. Okay? So now the resulting frequency, the spectrum, the spectrum of this h of the filter as a function of small omega. The spectrum is the convolution between G and omega and W. G and W convolve in the frequency domain. Sorry, this should be theta. Can we all change this to theta? That's wrong. Convolution in the frequency domain, and there's a factor of 1 over 2 pi. And here is a few remarks about our notations. Okay, a few remarks about our notation. First of all, here instead of ej omega, we simply write omega to emphasize that this is a function of small omega. Okay? You can imagine that this simplifies our notation quite a lot. This simplifies our notations. So that's my first remark. And then the second remark, I also emphasize that now this convolution of frequency domain is denoted by this star sign with a circle around. Some people also call it circular convolution, because actually the angle here is around the circle, a full circle. Okay, circular convolution in the frequency domain, so about which is defined exactly like this. All right, so now here's one more remark I want to make. Please be aware, note that both G and W are real valued in this case. In this case. And this will make it easier to plot the frequency response, which we're going to do next. Okay, in the next slide, we're going to see exactly what is it we'll visualize what's going on right here. Okay, when we convolve two things in the frequency domain. But first, I want you to notice that both G and W are real valued. Do you know why? Do you know why? Why are they real valued? Because here, first of all, we already know G is real valued. G, the ideal frequency response is real valued. But by definition. But why is big W also real valued? Because similar to G, it is an even symmetric function in time, right? Even symmetry in time, real in the frequency domain. So just both W and G are even functions. Therefore, their Fourier transforms, respectively, 各自的, their Fourier transforms are real values respectively. Both of them are real valued. Okay, so now we are going to finally see in this next slide. In this next slide, we will be looking at the convolution, the circular convolution in the frequency domain. Okay, so now just to point to, as a matter of fact, now here that's what? This is the ideal response. Okay. Which look rectangular in the frequency domain. Theta is the frequency variable. So let's rewrite. Here, my notation is a bit different. So my notation is h of omega equals to 1 over 2 pi. And there is a, what? G is my ideal response, G theta. And we need to flip and shift W. Flip and shift W. W what? Omega minus theta, d theta. Okay, and we say this is G omega circular convolution with W of omega. Okay. All right, so you have seen that now G is the ideal response, which is ideal, okay? And the W, this is something that we need to find out, okay? So it turns out that the Fourier transform of the window is not that hard to calculate. So we can show that there's some ripple-like. This is a periodic sinc function, by the way, okay? It's a periodic version of the sinc function. That's the Fourier transform of W, which repeats itself every 2 pi, okay? It's not that hard to make sure that this is indeed the case. It's real value. It can be go positive or negative. Okay? Positive or negatives. So now we want to imagine together. So I invite you to now let's work on this. Can you imagine what's going on when we convolve W and G? This is my G. Okay? When we circularly convolve W and G, what will happen? What will happen? So basically, we're going to take an integral, right? This is about calculating an integral. 做积分嘛, calculate integral. Okay? What is the meaning of an integral? Integral is the area below the curve, right? So basically, we are going to evaluate the area of W now flipped. Okay? We flip W, which turns out to the same thing because W is also symmetric in the frequency domain. Now, flip W and multiply it with H, flip and shift. Okay, flip W and shift it by omega. So imagine this curve is going to shift to the right and to the left. So we need to repeat this. Okay. So on this plot, we have the case of now. This is theta. Okay, when we consider convolution, and now this is W of basically theta minus omega. Yeah, and it looks like that. It looks like it's gonna have it like that. So we will calculate the area of W times G, with W being flipped, 左右翻过来, and shifted to the right by theta. Then you calculate one area, right? Now you can also shift W to the right and to the left. Let's say now, for the next frequency, we consider W omega is closer to the edge, okay? And then yet another frequency, we consider W now moving outside the passband. W now can move outside further to the right. That's also possible, okay? Or to the left. Now this is doable like that, okay? Moving W, I suggest I try to imagine now we're moving W to the right and to the left, because we need to do that for convolution, okay? And whenever we move it and move it and just, let's say, just move it and then just evaluate the integral. Move and evaluate the integral. And the result is shown right here. The result now has ripple in the passband as well as ripple in the stop band. That's the result. That's the result that we need to spend a few moments to contemplate. 凝视一下这个感觉啊。When we convolve the first transform of the big W and big G, do we really get this? Do we get this? It makes sense. Why? Because when W move outside the passband, W and G do not overlap much, right? Therefore, the area becomes small. But when the main lobe, later we'll learn that this major part is called the main lobe, okay? The main lobe, and we'll come back to this. When the main lobe is within the passband, the area should be large. When the main lobe is moving outside, the area should be small. And the area can also even be negative, depending on where exactly is omega. Okay, so please now when you go home, please convince yourself that indeed when we can visualize convolution like that, okay, by considering the area below a curve. Okay, so I think time is up. So see you tomorrow, and when we have a follow-up discussion.